Welcome, I'm Mulansky. I'm a physicist. I work at the Institute for Complex Systems in Florence. And my main funding is through the European Union within the so-called NET project. So I should always acknowledge my funding. But today I'm not going to talk about my research. I'm going to talk about how I can get my research to run faster, essentially. And there are some techniques that I came across, and I'm very happy to share those. So just a short glimpse on what we are going to see by the end. So I will do some single core performance improvements of my simulations. And I will use two techniques. The first is to implement everything in a way that it makes more efficient use of caches. And then on top of that, I will use the SIMD instructions. And you can see that you can get up a speed up of more than a factor of 3 if you use those techniques. So bear with me for the next 45 minutes or so. We will end at this point. Okay, so everything for me today is about performance. And when I talk about performance, what I mean is in the sense of numerical simulations where we need flops. But actually what we need is simulation runtime. So I mean, in the end, I don't care how many flops I measured. I want my simulations to end as fast as possible. So what I'm not going to talk about at all is database queries, response rate, latency, like all those kind of things is not my performance. Okay, so there are two essential performance bounds. The one is the plain CPU power, which means how many floating points per operation, floating point operations per second can I get out of my CPU. And the other performance bound is the memory bandwidth. So how much data can I get actually into my CPU to work on per second. Okay, so in a short structure of my talk, first I will introduce the problem that I'm working on. I will talk a little bit about the CPU limitations. And then I will mention the core problem of memory bottleneck, memory bandwidth bottleneck. I will show you a bit the numerical algorithm that I'm working with, which is an ODE solver. And then finally, I will come to the point where I will try to show you some techniques how to turn this bandwidth bound implementation into a flops bound one. And then if we reach the flops boundary in the CPU, we can actually go ahead and get more speed out of it by employing Simdi instructions. Okay, so short disclaimer, so this talk is a bit of a hybrid. I give this talk in front of physicists as well as in front of C++ people. So there are maybe some parts in here that are not so interesting for you and some parts because you know all of this already. But on the other hand, I will talk about some physical problems. So I hope I can get everyone on board on what I'm going to talk about. But if there are any questions, please feel free to ask. Okay, so first part is about the cache optimizations. So the problem is, as I already mentioned, in current CPUs, you have a lot of flops. So you can get very easily, on a 3 gigahertz CPU, you can get 1 operation per cycle. It's a reasonable assumption. You can get up to 3 gigaflops. But you also have to get the data into your CPU, and that's where the problem starts. So I just took specs from the Core i5 CPU in my laptop, which has some 16 gigabytes per second from main memory. And if you do a simple operation like vector addition, you need to transfer 24 bytes for every operation you do. And if you want to reach 3 gigaflops, that means you need 72 gigabytes per second. It's simple math. If you only have 16 gigabytes per second, all you can get, theoretically even, so the theoretical limit of your performance is less than 1 gigaflop per second. So this is exactly the core of the problem. Now, obviously, CPU designers figured it out already, so they gave us caches, which are much faster than the main memory. So you have in modern CPUs level 1, level 2, level 3 cache. They have increasing size, decreasing bandwidth, and increasing latency. Okay, it's the usual trade-off. But if you have to go to main memory, I mean, it breaks down completely. So whenever you have to go to main memory, things get horribly slow. And I'm not even talking about if you have to put stuff on the hard disk, I mean, then you're just lost. Okay, so this is the problem, and the solution are the caches, but now we have to make use of the caches in the most efficient way. Okay, so that being said, let me introduce the numerical problem that I'm dealing with, which is the ordinary differential equations. So they are written in this very general form. You have the time derivative of some state variable, and you have given this as a function of the state variable itself and possibly of time. So this is the most general form of an ordinary differential equation. So keep in mind that the state here can be a vector and it can be a huge vector. I omitted vector notation here, but it's implicit. So what we then usually are facing is a so-called initial value problem, where you have the state of your ODE or of your system given at some time 0, and you want to evolve in time. So you have to somehow, from this state, you have to go forward in time, compute the trajectory, which is usually denoted as r of t. And the most simple thing you can imagine here is, for example, like a pendulum, which you can describe as an ordinary differential equation, and you have some starting position. And then if you compute the time evolution, you will see that the pendulum starts to swing, for example. Or any dynamical system in that sense can be described as an ODE. So in physics, it appears everywhere. For example, also neural networks, which I'm currently working on in computational neuroscience. It's just one huge, gigantic network of ODEs, essentially. So this is an everyday problem in physics. And I spent my whole PhD solving ODEs, and I'm spending my time right now still solving ODEs. So this is a crucial problem in numerical physics. Okay, so the problem is that you usually cannot write down a mathematical analytic solution of such an ODE. Sometimes you can. For example, the pendulum, you can just write down, okay, it's a sine function, cosine function. Maybe you can even do it if you have friction, then it's an exponential decay in front. But if it gets even only slightly more complicated, you're completely lost analytically, so you have to do some numerics. And the way this works is you introduce a time discretization. So you go from continuous time, you go to discrete time, where you go from time point 0 to time point 1 to time point 2 and so on. So you iterate forward in time, and you have some numerical approximation that gives you, given the current state, it approximates the next state with a discrete time step. So this is illustrated here, or you can, okay, this x is what I call r up here. So it's not very consistent, but I hope it remains clear. Or if you look at it in phase space, where you just plot the different components of r, and then you see the whole trajectory in phase space. So this is what physicists like to do, put things in phase space. Anyway, so this is, let's say, the numerical thing we have to do, and you can see that this can get very time consuming if you have a huge system of ODEs and you want to iterate the solution forward. You have to go to time step 1, time step 2, and sometimes you have to do like 1 trillion time steps until you reach the end of the universe, if you do astrophysics simulations, for example. So there's a lot of numerical efforts put into these kind of simulations. I don't know if you heard Thomas Heller's talk this morning, so he had some examples. So for example, weather simulations, if you want to know what's the weather going to be like tomorrow or next week, it's also essentially ODEs that you have to solve numerically. Okay, so this is the problem. Now, where does cache come into play? So I have a very simple, trivial example that illustrates how this can create problem. So suppose you have a system of n small and independent ODEs. So let's say we have a system of 1 million penduli, that you, pendulums, I'm not sure, that you want to iterate, and you want to iterate all of them. Okay, because for example, you want to do a parameter study, so you change one parameter and you want to know this for 1 million parameter values, what changes when you change this parameter, or you have different initial conditions and you want to understand how this affects your trajectory. So this is also realistic questions that we ask in physics, not for pendulums, obviously, but for some more difficult problems, this is not trivial to answer. So this is a problem that we actually do face, and it's easy because all of those pendulums are independent. So I can first look only at the first pendulum, iterate this until the end of time, and only then I go to the second one and I iterate this forward, and so on. So this is what I here call the time-first approach, where I look at each of them after each other. Or the other idea you could think of is, okay, I take all of those pendulums, I put them into one huge state of my system, and I iterate all of them forward at the same time until I'm done. Okay, so now the question is, which of these two approaches is numerically more efficient? So the second one? No. So here I measured the actual performance in terms of flops per second of those two approaches. Blue is the time-first approach and green is the vector-first approach. And as you can see in the beginning, they're more or less equal. The vector-first approach is even indeed a bit faster, but if you increase the number of systems, so the system size, which I measure here in bytes for simplicity, you see that at some point the vector-first approach starts to slow down, and then it gets really bad. And the reason exactly is because at some point your huge system doesn't fit in cache anymore. And that means whenever you iterate, essentially you do two iterations. You do one iteration over time and one iteration over the whole bunch of systems. And the question is what is the outer iteration and what is the inner iteration? So the first approach is the outer iteration is over time and the inner iteration is over space. And the second approach is exactly reverse. So the outer iteration is over space and the inner iteration is over time. No, I got it wrong, I think. In the first approach, the outer iteration is over space, inner over time, and the second approach is the other way around. And the problem is if you do the iteration over space in the inner loop, then what you essentially do is you get some bunch of memory, you do one time step on this bunch of memory, and then you have to throw it away. The next bunch of memory, you do one time step, and then you have to throw it away. But if you do the other approach, you get one bunch of memory, you get it in your cache, and you iterate and iterate and iterate and iterate for a long time until you're at the end, and only then you throw it out and you get the next thing into cache. So, I mean, from this very simple description, I hope it's clear that you have to look into the main memory much less often than for the other approach. And this is exactly what you can see. If I draw lines at the cache sizes for these simulations, you can actually identify that as soon as I reach L2 cache size, I'm getting a clear performance drop, and then if I'm reaching L3 cache size, I'm going down even more. Okay, so if my system is too big to fit into cache, then I have to pay a huge price if I do the vector-first approach, because I'm essentially looking into main memory all the time. Okay, so, well, lesson learned here is do the time-first approach. Okay, pretty easy. Just get things into cache, work on it as long as possible, then throw it out, and then only then look at the next thing. Okay, but this problem is actually, so the simulation was very simple because all of those systems were independent. Now what I'm actually faced with is a similar setup, but now I have a huge amount of pendulums, but all of them are connected to the nearest neighbor, right? So I have some local term, so I have my pendulum term that makes it swing, but I have a coupling term, so if this one swings, then it's in some sense connected to its left and right neighbor. So if this one swings, then the right neighbor will start to swing also, and the left neighbor will start to swing. So there's a local coupling between nearest neighbors of like chain of pendulums. Okay, is this setup clear? I hope. Again, we do the numerical approach. We discretize time, and we do a time evolution from one time step to the next one. But here, okay, let me go a bit more into detail because this will become important now. So what I'm using for this time evolution is a so-called Runge-Kutta algorithm, which does, okay, it takes the state of the system at time t, it does some rather complicated computations, and it gives me the time at the next state. And within this rather complicated computation, it actually consists of several stages. So it computes one intermediate value, from there it computes another intermediate value, In total, depending on which exactly you choose, you have some number S of intermediate values, and those give you, in the end, the final approximation for the next point in time. Okay, so this is how these numerical algorithms work in general. Okay, so this is in some way graphically represented here, and if you have nearest neighbor coupling, then to get those intermediate values, you always need the pendulum itself, but you also need the state of the nearest neighbors, because they influence the pendulum in the middle. So all of them are connected to their neighbors. Okay, so whenever I compute some intermediate value out of the current state, I not only can look at my pendulum itself, but I need also to look at the neighbors. And this creates a huge problem, because due to this coupling, I cannot just use the time-first approach, because I cannot take the first pendulum, iterate forward forever, because for the next step, I actually need the result of its neighboring pendulum from the previous step, right? So if I want to do 2 time steps at the first pendulum, I better have already calculated the first time step of its neighboring pendulum, and so on. So I cannot use the time-first approach that I just found out was the best. Okay, so if I have this kind of coupling, I'm stuck here. So of course I can do the vector-first approach and just buy more computing time, but I want to do better. And the idea is to introduce clustering. And what that means is I take my huge system of pendulums and I divide it into chunks of such size that they fit in some way into the cache. Okay, let's say I have 1 million pendulums and I take the first 1,000 and I work on them, and then I take the second 1,000 and I work on them, and so on. And if I work on the first 1,000, then I can almost all of them, I can exactly iterate forward, because almost all of them have their neighbors within the chunk. The only problem I have is at the edges, where I don't know the time evolution of the nearest neighbors to the left and the right. Okay, so what I do there is I simply, if I want to calculate the time evolution of 1,000 pendulums for 5 steps, then I take 1,010 in total, because I add 5 to the left and 5 to the right, and I iterate all of them forward, but then I make a mistake at the very left and the very right boundary. So here I don't know the neighbors, so this is going to be wrong, but all others are correct for the first step. Okay, and then I do another step, and then because this was wrong, now my mistake travels inwards in my state, but all of those are still correct. And now I have 2 mistakes, 2 wrongly calculated pendulum on the left and the right. Okay, and this I can do for S steps. And if I had added S additional pendulum to the left and S to the right, then at the end I will have exactly my 1,000 correctly iterated pendulums in the middle, and I just throw away the rest. Okay, so this is the whole idea that I can do if I have this nearest neighbor coupling. Okay, and the idea, well, the main point here is obviously that I want to by working on those 1,000 pendulums for many steps, I reduce the memory bandwidth and I increase cache utilization. But yeah, I mean, nothing is for free, so I have to pay a price for this. And the price is exactly that I added those pendulum computations on the left and the right that I have to throw away in the end. So I do some extra work of some wrong results that I don't really use because they're wrong. So I do additional computations that I'm not gonna, that are not useful for my final result. And there's another problem here, which is that how big should I make my cluster size? So I have an additional degree of freedom which I can play around with, and it's not a priori clear which optimal granularity I should use. I mean, I can get a rough estimate from the cache size, so that, I mean, I can be sure I shouldn't make my cluster too large so it doesn't fit in cache at all. But if I make it too small, I have too much overlap computations, so I also don't get any performance gains. So it seems natural to assume that there's some optimum somewhere in between. But to actually find this optimum, I will do some measurements and actually look at the performance to find out what is the optimal granularity size here. Okay, yes?
Is overlap size depends on the cluster size or is it independent?
The overlap here in my 1D, so I have a one-dimensional chain, it's independent. It only depends on how many steps I want to make. So if I make 5 steps, I have to add 5 additional. If I want.
So theoretically, this also affects the cache, the size you cache or the cache you have to use, right?
Yes. Yeah, everything has to fit in cache.
So both like cluster size and overlap.
Yes, exactly. But I mean, as we will see, typically cluster size is on the order of 1,000. Overlap is on the order of 5. So I mean, cluster size is dominant here. But it's a very good question. So if you do the same thing in 2-dimensional simulations, we can maybe talk at the end about this. Things get a bit more complicated because there, the actual overlap depends on the size. Because one thing is linear, the other thing is quadratic. It still works, but this is just the simplest and cleanest one. That's why I'm using this as an example here. Okay, so far so good, I hope. Let's look at some performance results, some details on the actual problem. I'm not dealing with pendulums. I'm dealing with so-called Rösler systems, which is a 3-dimensional system with a chaotic attractor, blah, 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 fancy physics. I work with 1 million of those, which means they take up 24 megabytes roughly. So these are the equations for one of those Rösler systems. And here's the coupling term. Okay, so if you set D equals 0, you have just uncoupled Rösler systems, and you can do the time-first approach. But here you have this nearest neighbor couplings. It's a diffusive coupling, and well, I mean, there are some reasons why we're interested in this, but this is not the point of my talk. Okay, I run simulations on a rather new Intel Xeon processor with almost 4 gigahertz. I'm using Intel compiler. And I measure performance with this really cool so-called liquid framework, which gives you nice and rather easy access to the CPU's performance counters. And here you can, I don't know if you can see it here, for example, you can check how many megaflops per second your performance was employing. Okay, so this is, let's say, my setup, and here are the results. So the first thing I want to find out is what is the best granularity. So I do several runs for different sizes of my clusters, and as you can see, gigaflops per second are not very impressed with this granularity size in here, but due to the overlap computations, if I have a very small granularity, I get, so this is the, okay, I should probably say what you're seeing. So this steps per second means actual simulation steps of my whole system in real time seconds, so wall time on the CPU. And As you can see, if I have a very small granularity, then I have lots of overhead computations, and I get the same gigaflops per second, but most of, or like a large fraction of those flops are spent on overhead computations that I'm not going to use anymore. So my overall steps per second is smaller. And at some point, I can identify some maximum, and I'm using this. And you also see that as I increase my cluster size, at some point I reach L1 boundary, and I have to go into L2. And you see that you can, from at 16K of cluster size, I slowly start to have to go to L2, but it's not too bad. It doesn't affect my CPU throughput, but because L2 is still fast enough. Okay, so this is how I identified the optimal granularity size. And then I can compare this to the standard implementation, which is vectorfirst. And you see that I get a factor of roughly 2.5, I suppose, well, more than 2, definitely, in actual performance, in steps per second. Also, the gigaflops go up by roughly a factor of 2. And the reason you can see here, while the standard implementation has a lot of traffic on to the L3 cache, which essentially means it has to go to main memory, because everything goes through L3, what comes from main memory. And if I introduce my clustering, you can see that L3 goes down a lot, and L2 goes up, but L2 is fast enough, so that's okay. And I essentially succeeded to turn my bandwidth-bound algorithm into a flops-bound one, because I reached some 4 gigaflops on a 4 gigahertz processor, so this is roughly what you would expect from a normal FPU to be capable to deliver. So right now, I claim that, okay, now I have reached the CPU throughput boundaries in my algorithm. So what I want to do next is to make things even faster. And the way I can do this is by utilizing the Simdi instructions that the modern processor all are shipped with. And the main point I have to stress here before I go on is that if you have a memory-bound problem, Simdi instructions don't help you at all. I mean, the only thing they can do is to increase the CPU throughput in terms of flops per second. But if you don't have enough memory bandwidth, and if your algorithm is bounded by memory, then it doesn't make any sense to look into Simdi. So before you start looking into these kind of optimizations, you really have to measure what exactly is the problem in your algorithm that makes it slow. Okay, so well, a short one slide on what these Simdi instructions are. Essentially, you have special registers in the CPUs where you can put, let's say, 4 double values in, and you do 1 operations on all 4 of them in 1 cycle. So essentially, you can go from 1 floating point operation per cycle to something like 2 or 4 or 8, depending on your CPU. Now, in a perfect world, the compilers would be capable to employ those things automatically. And Chandler yesterday somewhat claimed that they are already able to do this, but in my experience, they are not really good at that. So if you start doing this explicitly, you can get a lot of performance gain out of those special instruction sets in modern CPUs. But again, I already stressed it. It's only helpful if it's actually flops bound. Otherwise, it doesn't help you at all. Okay, so if you started to doing this by hand, you would have to write different code for different processors, different instructions that provide different instruction sets. So this is something I stole from somewhere, so I don't even understand what's going on. But this is kind of what the code would look like if you would do Simdi by hand. Okay, depending on if you run on an Intel or Altivec extensions, everything looks different, and it's a huge hassle to do this. So what I decided to use is this boost Simdi library. Well, it's not officially boosted. I just talked to Joel, and he told me they're currently moving it out of their huge NT2 library, and they aim for boost review next spring. So, but he told me this 2 years ago already, I think. So let's hope it's going to happen. I mean, it's a really cool library, so I really would love to see this in Boost. So what it essentially does, it gives you a C++ abstraction of all of those Simdi instructions. So it supports everything that is there. I mean, I actually stopped here because I didn't want to spend more than one line on my slide. But so everything that exists is supported essentially. And the fundamental way this works is they have an abstraction for these SIMD registers into what they call a SIMD pack. And then they use some expression templates. I don't know, some of you, I'm sure, saw Joel's talk just before the break, where he explained some of those details, how they implemented this. But the main idea is that you can keep your usual C++ abstraction between containers, iterator approaches, and algorithms, and SIMD fits, or this SIMD library fits very nicely into modern C++ development. Okay, the fundamental entity here, as I said, is this SIMD pack, which is can be of an integer, float, double, anything that is essentially an integral type. And you can, if you want, you can specify the size of the pack. But I don't know why you would do this, because it's actually done for you by the compiler, and it depends on the platform you are compiling for. So if you're compiling for, if I'm compiling for this machine, it would be 4. For example, it can fit 4 doubles or 4 integers. If I'm compiling for an older CPU, it can only fit 2. I don't have to worry about this. This is done by the library. It figures out what is the target platform and uses the right number of the right size of the SIMD instructions. I mean, it has to be a power of 2, but again, you don't really have to worry about this. And then, so what this library actually does, it provides you all the mathematical operations on those packs, including all sorts of mathematical functions. So you can essentially replace your type def of, let's say, double by a type def of SIMD pack of double, and then just write your algorithm regularly, and it automatically does all the computations using those SIMD instructions. And if some are not implemented, it just falls back to FPU, so you're very safe. So this is more or less the approach. It uses expression templates to implement this, but Joel just had a slide where he said, don't talk about expression templates, so I'm not going to talk about expression templates. It's just an implementation detail on how all of this is done, and it's really nice from a user perspective. It's not so nice from a compiler's perspective, because it creates huge expression trees, and your compile time can go up quite a bit if you have a rather complicated expression involved. But there are some benefits. So if you have the whole expression available, you can fuse some of them together, and use those fused operations that are also available in these SIMD instruction sets. And, well, it's easy. With easy, I mean actually it's possible to incorporate your own extensions and your own stuff into these kind of libraries, because everything, you just have to specialize certain template operators to get stuff in. Okay, but the whole purpose of this slide is that you don't really have to worry about all of this, because in practice, you just write your algorithm as usual. You use the normal operators on those SIMD packs, and everything should be fine. But that's not, as usual, that's not completely true. Because you have to worry about alignment a bit. And the reason is that if you want to use if you want to use SIMD registers, and you load stuff from main memory in there, the stuff has to be aligned properly to nicely fit into the SIMD register. But all you have to do essentially is use the correct allocator that's also provided by this library. And if you do this, you're good. If you don't, and this is what I forgot the first time, then you write an email to Joel, why is this not working? And he writes you back, yeah, you have to use the allocator. Okay, so this is the only thing that didn't work right from the start for me. Everything else was really smooth and very easy and simple with this library. Okay, so if you want to implement, let's say, vector addition, so here's the straightforward non-SIMD approach. You just use a vector of doubles, you use a for loop, and you calculate whatever you have to calculate. Now let's implement this using SIMD expressions. And the only thing I have to change is the type def here. And I have to change it in the following way. Now I'm not working on doubles anymore. I'm working on SIMD pack of doubles. I don't have a vector of doubles. I have a vector of such packs with the correct allocator. I'm getting the pack at compile time because I'm not specifying it. It depends on the CPU I'm compiling for. So let me get this as a compile time parameter out here. And then because now in this pack I already have 4 doubles, I only have to worry about, my vector size now is the total number of values I want to work with divided by the pack size. Yes?
Question, the pack static size, the pack static size, is it independent of the actual type? Is it independent of being a pack of double?
No, it's not.
Okay,
because
just
no, so the pack, the pack here knows that it's a pack of doubles.
But the lower one doesn't.
No, but this pack already does. The pack already does. Yeah.
Also, I have a question. So if you have a vector of packs, then if you like index into the vector, you do like a vector 3 or something. You don't get the third number, you get the third pack. How do you actually get the doubles?
And then, it's like a tuple. You can access the pack. You can look into the pack like you look into a tuple, if you want. So you have compile time access and runtime access. Both kinds of indexing into the pack are supported.
So you change the semantics of the vector essentially, right?
Yes, sure. But yes, I do change the semantics of the vector. But okay, we will see later the implications of this. Okay, so as you can see, all I have to do is change the type def essentially, and then because my algorithm looks exactly the same. So the for loop does exactly the same thing. And this is essentially maybe related to your question. I don't have to look into the pack anymore. I just work on the pack as a whole thing. And this is, SIMD instructions is single instruction for multiple data. And this is, let's say, the algorithmic representation of this idea, because I can only do the same operation on the whole pack as such. I cannot do a multiplication for the first entry and an addition for the second one. Then I cannot use SIMD instructions if I want to do that. Okay, if I write this in terms of a transform, it's even, I think, more beautiful because you have even the for loop away, like the usual approach. This is a slide for physicists, essentially, so maybe I can skip over this with this crowd. The key message here, again, is you change the type defs, but you don't have to touch your algorithm, really. And this is what Boost SIMD essentially gives you. Okay, now how does this work for my ODE simulations? Well, if you think about it, then this iteration from the whole state at time t to some time t plus delta t is essentially some fancy form of a transform. And so the approach I just showed you can be, in some abstract sense, be applied to this problem as well. So the way I'm doing this is I'm using the Boost ODE library, which is developed by Carsten and myself. And it provides you a generic implementation of all of those ODE's algorithms. It's container independent, so I can, instead of vector of doubles, I can just put in a vector of packs, and it works very nicely. I can also exchange the backends if I have to, but with these Boost Simdi library, I don't even have to exchange the backends because like the usual approach of just operators and iterating works perfectly fine. Okay, so if I implement things, if I implement my simulation with Boost ODE not using Simdi for now, I declare my state type, what kind of algorithm I want to use, Runge 4, and then I have this integrate const which just iterates forward. So this is essentially my transform in some way. Now if I want to employ Simdi instructions, again, the only thing I have to change is some type defs in the beginning. So if you look here, this is my algorithm of ODE integration, and it's the same down here. So again, I only have to change some type defs. I have to make sure that I'm not computing 4 times too many values by reducing my vector size accordingly to the pack size. But the actual implementation of my algorithm, I don't even have to touch at all. And essentially what's going on is it's a bit of a reorganization of the data so that it fits into the Simdi registers, and then it just does all the computations on Simdi using Simdi instructions. Okay, so let's see how this works. So I'm going back to the very first example of completely uncoupled systems where I used the Timefirst approach, which was flops bound. Boost ODE and Boost Simdi, it's actually these performance runs, I made them part of the ODE library, so you can actually find them online. I'm running on this laptop because I did this yesterday using Intel compiler, and here is what you get. FPU on this machine gives me almost 4 gigaflops, and if I do the same stuff with the Boost Simdi library, I get up to 13 gigaflops. And all I had to do is some type defs. I mean, it's not completely true. I left out a few things because you have to do initialization, and in the end you might want to calculate some things. So at some point you have to look into these Simdi packs. But the core of the algorithm, like the iteration forwards along the trajectory, is all done on Simdi registers, and for this you just have to add some type defs. So I mean, with like almost no additional coding, you get a factor 2 or 3 increase. So here I'm looking at the flops, but what I'm really interested in is the speed up of the actual runtime of my simulation. So I looked at this speed up, and you can see that I get a factor of 3 by using these Boost Simdi expressions. Okay, but this is not what I really wanted to do. I wanted to increase performance of my cache optimized stuff. So let's look at how this works. Again, those coupled systems with nearest neighbor coupling, I'm using already the cache optimized version that I presented before, where I was convinced that it was flops bound. Again, based on Boost ODE and Boost Simdi, and the source codes, I already published them on my GitHub. So if you're interested, you can see things there. Here, those circles are exactly the results I showed you in the beginning. So FPU based calculations for different granularity sizes. So essentially the cache optimization we had before. And now the squares are additional SIMD instructions. And you can see it's here much more sensitive to the cache size. But again, I can figure out optimal granularity, and I use this to compare against my previous implementations. And you see that now using this cached optimized version and Simdi instructions, I get a factor of more than 3 of overall speed up. I'm on this CPU, I'm reaching 10 gigaflops almost. And well, I mean, I have a bit more of L2 memory bandwidth, but I'm still flops bound, I think. But I'm not sure about this here, actually. Yes, there's a question?
Yeah. Why do you need more
Why is the cache performance worse?
I mean, you go through L3 more than without it, right?
Here.
Because it's faster, or is it?
Here.
Yeah.
Yes, because it's faster.
So it's faster.
Yeah, exactly. If I increase my flops, I also need more data to come in. So.
Let me rephrase. Why
Okay.
is the sweet spot a different one for SIMD than for?
This is a good question. I'm not sure. I'm not sure about this. So this sweet spot here, it's not very distinct. I mean, here I'm not really, okay, so I'm not, for the FPU based version, I'm not very confident that I really found the exact sweet spot. But I'm not sure, okay, so this is some artifact. I don't know, I cannot. I'm not sure about that. Okay, so this is essentially what I managed to do. For completeness, so all the results I showed you before were for one particular overall system size of 24 megabytes. So for completeness, I redid all these simulations to check how this depends on the overall system size. So I go from very tiny systems to almost 2 gigabytes, like lots and lots of those Rösler systems. And I measured the performance gain, and I divided it into like what do I get from cache optimization and the additional stuff I get from Simdi instructions. And I checked for Intel Xeon as well as AMD Opteron. And on both processors, I got similar speedups of roughly factor 2 to 3, depending on how big is my original problem size. If I have a very small problem, obviously that fits into cache anyways, then cache optimization doesn't give me much, but Simdi instructions is still useful. But if my problem gets really, really big, I really have to do cache optimization before I can even think on employing Simdi instructions. Okay, so let me quickly summarize. So I showed you that by introducing granularity into your simulations or into your algorithms in general, you can manage to reduce the data transfer to main memory and therefore turn a bandwidth-bound problem or a bandwidth-bound computation into a flops-bound one. And if you've done this by increasing the operations per cycle using Simdi instructions, you can get a huge performance gain of a factor of 3 that I was able to achieve. Now this idea of clusterizing and granularizing your simulations is actually not, it's not my invention. They do it for stencil computations since a long time, and they call it space and time blocking. So I just essentially adopted this idea to ODE simulations, and here I have actually an advantage even because in my Runge-Kutta simulations, I anyways have to do a certain number of internal steps that I can. So it's completely transparent from the outside that I'm doing this clustering, essentially. So if I use this program, anyone who uses this type of simulation will have exactly the same kind of results or the same interface to the results than if you do it straightforward, because the different stages internally are there anyways, and they are completely hidden from an external user. So this is actually better than for those stencil computations where you have to fuse stencils artificially, and then you only have access to the correct results every 5 or 10 steps. So here I have actually an advantage in my ODE simulations over the classical problems. So the take-home message would be if you have huge data sizes that doesn't fit into L2 cache, you have to think about introducing granularity to reduce the memory bandwidth problem. And always write generic algorithms because it makes it so much easier on the long run. You can just, for example, this is just one example where you just throw boost Simdi at all of your stuff and you suddenly get a performance gain of factor 3. As I mentioned this, so the source codes are available online, and it's really, really simple to implement if you have these high-level libraries available that work very nicely together. So the whole simulation with cache optimization, Simdi instructions, and everything are roughly like 200 lines of C++ code. So it's really, really simple to use those kind of things. Okay, with this, I thank you very much for your attention, and I'm open to questions. So there's...
When you have shown the clustering, you made fixed sizes of clusters, and the number of valid results is shrinking in the middle. You could otherwise also make the cluster in the beginning bigger and end with, you said, 1,000 valid results. I think it doesn't matter much. Have you tried both variants? Is there any difference in the complexity of the code?
I haven't understood. What were the two variants?
Okay. You said you have many results on the left and right boundary that you have to throw away because they're not valid in your approach. And
Yes.
it would be an idea to just make the beginning wider, so you end with a result of 1,000 valid values.
So
Yes.
instead of
Shrinking your size and you have to recompute the invalid values later, you just start with a bigger size and end up with enough valid values.
well, that's exactly what I'm doing.
Okay.
That's exactly what
That
I'm
was the question. How do you implement it in detail?
Yes, in this, so I start with a bigger slice, and I throw away left and right stuff, and then I end exactly with what I wanted.
Your
to
slide
happen.
suggests that you do it, you recompute the missing values
Yes.
later. So, okay.
Yes, exactly.
Okay.
So what? So first I do the first cluster, and then I have some additional ones over here that I'm going to throw away, and the correct ones for those I'm going to compute later. But then I'm computing additional ones over here that I'm again throwing away.
Okay.
But it's, I mean, at some point I have to throw away
No
stuff.
big difference. Yes.
No, I don't think it's a big difference because you have to compute those things and you have to throw them away essentially.
Okay. Thank you.
But you can remember the overlapping part for the next iteration.
Well, I mean, if they're correct. I mean, here, I mean, if they're just plain wrong, then I don't want to remember them. I want to, I mean, because they're just not the correct results.
Can you open the next slide? Maybe one more. And yes, this. My question is about the graph with the cache bandwidth. I'm just interested, how did you measure it? With which tool?
With this one. So this one, I mean, here you see, I can tell this guy what I'm interested in. So here I'm interested in flops, so it tells me the flops. But I can here put L2, and then I get the L2 memory bank. Well, the L2 usage, essentially. So this is Liquid, is the tool I'm using to access the performance counters, and there are performance counters for L2 and L3 and L1 and main memory and all those things.
No, it's clear. Thank you.
There was one over here.
I just want to ask, what are you exactly doing after this S steps when you run out of overlap? When you finish like one stage. After this S steps, what are you doing? You are like merging the results, or?
So in this simulation, I'm not doing anything. I'm just doing the next time iteration. So I want to get to the end of my trajectory as fast as possible. But what you would, for example, do, I mean, one thing is you measure Lyapunov exponents, for example, which is something in chaos theory. Then you would have to do, after you do all of this, you're interested in some growth rates of small deviations and all kind of things. Here, I mean, this is just a like simplified basic simulations where I just iterate a trajectory forwards. I don't do anything in between.
So basically S is equal to number of steps?
No.
No?
No, that's not correct. S, so that if you want, I have two clusterings here. So one clustering in space and one clustering in time. So I take the first cluster in space, I put it in my cache, and then I do S iterations on this cluster. And then I throw it out, and then I get the next cluster in space, and I do S iterations in time in some way. And then if I'm at the end of my space, I go to the first one again, and I do the next S iterations in time.
So how big was S for your
S
simulation?
was here 4. 4 steps in time. So I have 4 on the left and 4 on the right additional values.
Sorry for this. So first of all, thanks for the talk. I got a question. If you're done with your SIMD computation, so for your case, you were done with this, right?
Yes.
Or so my question would be, if I need to do some computations where I cannot work on the pegs, how should I like leave the memory aligned as it is, or should I copy this back to a normal vector and do my computations?
No, you can leave it as is. So I mean, maybe you should ask more experts on this actually, but my approach would be, for example, if you want to compute the overall average of the first component or something, and then you can average over the pegs, but then you have 4 average values that are representing like the first index of the peg, the second, and so on. And then at the end, you have to average over those 4. And for this, you have to look into the pegs. But you don't have to copy it. You can actually, yeah, well, he's already. Yeah, okay. No, so I mean, okay, so the main message is do as much as you can on the peg. If you can't do things on a peg, then ask Joel first. And if he can't help you with that, then you have to look into the peg. But you don't have to copy it anywhere. You can just access it.
But the memory is contiguous in the
Yes.
container also.
Yes.
Hi. Have you made any thoughts into offloading some of these calculations to the either dedicated GPU or maybe Intel integrated graphics or something like that?
Sure. I mean, I also do stuff on the GPU, and this is actually an example which would also be suitable to put things on the GPU. But here, I mean, actually, I don't really need this performance in my simulations. I can just, it takes 6 hours instead of 2, but anyways, I will have the results tomorrow. So it's really just essentially a hobby or like my interest to do this. And here my interest was, learn about Simdi instructions, and I realized that it doesn't make any sense before I don't get the cache optimization right. So this is like my motivation here. Obviously, this is also a very nice example that you could put on the GPU, exactly. But it was not my main concern here.
Another question about this clustering. So I was wondering if you had looked at different approaches to do this. Since you're computing so many intermediate results that you throw away later, I was asking myself if a kind of cache-aware dynamic programming approach could yield. So I would think you would have almost the same cache awareness, but then you do not compute any intermediate results you have to throw away. So basically it means like going diagonally.
Yes, exactly. So what I can even do this here, I was just too lazy to implement. So to be honest, so I don't really have to calculate this wrong value. I can just not calculate it and just use this one. And here I don't calculate these two and only this one. And then I reuse them later on. And exactly, so this means roughly going diagonally through your thing. And this is actually definitely an improvement because I'm doing less overhead computations, but it's more difficult to implement, so I stopped here at this point, but yes.
Because for that you wouldn't need to cluster anymore. You could just use the whole thing and start at top left and go right.
No, you still need to. I mean, you still need to make sure that you don't go out of your cache.
Yeah, sure, but you can do this if you just stop vertically and you know exactly how many rows down you have.
Yeah, probably. Okay. Yes.
But about that, I would like to point out that if you combine this with the SIMD approach, then it's actually better to do it this way because you throw away computations that happen simultaneously with other computations that you're going to reuse. And the branching is going to kill your SIMD performance in that case. So this is probably better if you combine it with SIMD.
Okay. Yeah. So I got lucky, essentially.
You mentioned you're doing things in 4s. Have you tested on AVX or AVX3 hardware? Do you get a doubling of performance again?
I mentioned I do things where?
In packs of 4.
Yes.
Yeah.
So this is AVX, yeah.
So have you tried with AVX3 with a 512
No,
bit?
I don't. I mean, if you give me a computer that has that, I mean, I have to use what I own, or well, I don't even own this. This is some access that I still have from some university I was like 1 year ago. So I mean, I had to use what was there, and this is all I could do. So no, this is the only things I have.
Maybe a question to Joel. When will we get a boost SIMD out of?
I should have not come. Plan is to get something. Oh, okay. Sorry for hijacking your presentation. So, well, so BoostCMD is currently integrated into another project. We worked hard this year to get something for, let's say, first quarter of 2016 done, and have a review in the following month. So normally between January and March, we should have something external. It's already, I mean, we are working on it. If you look up, you can find a BoostCMD GitHub repository, but it's not full yet. But it's where all the things will live later. So yeah, it's definitely happening this year. If not, I'm fired anyway. So.
There's another one.
So another probably boost SIMD question. So I'm not sure. So I guess with this stuff, for example, the pack size, or whether you use like AVX or SSE or whatever, is a compile time choice, right? So exactly. You know you want to run your simulation on that machine, you know exactly what machine it is, so you compile that.
Yes.
The problem is if you do like, for example, commercial software, you have like, you want to build like a binary that should run like on any Windows machine, for example, and then you want to use whatever instruction set is available on that particular machine, but you have to do it at runtime, yes. Basically. So is there anything in BoostCMD to solve that problem, or how does
maybe
that work?
I can quickly answer. It's not my problem, so.
Yeah, but it's like, I think one of the main problems you have to solve if you do, like I'm doing audio software, for example, and this is like something you have to solve, otherwise it's not usable, basically.
No, I don't know about that, so. I don't do commercial software.
We made a deliberate choice to have a compile time at hardware selection for performance purpose. So what we usually do when we want to solve this exact problem, so we have a runtime functions that tell you exactly at runtime which are the list of extension the current CPU supports. So what we usually do when we integrate BoostCMD into other products for our clients is you write your kernel in a generic way. And this kernel, your functions that do your computation, okay? You write it in a generic way, and you compile the same code with different architectures. You can actually link all together, either in your SO or in your static stuff. And your main function just say, I'm calling BoostCMD is this stuff supported, then I call this one, or you use a switch or whatever. And usually your computing function should be big enough to offset this runtime selection, so usually it's okay. We tried once to have a runtime detection in each function, and of course it was a mess. So we went back to that. So write your function so you can actually recompile it with different set of instructions. That means that you probably want to use the pack without any fixed size, okay? And then you just link everything and ship this and select at runtime into some kind of driver function.
Hi. So I have a question. I guess you did your benchmark on a single-threaded.
Yes, exactly. All of this is single-threaded.
Did you notice if it scales the same if you do it like in 4 threads, especially combined with SIMD? Do you start hitting level 3 cache, or I don't know?
I didn't check at all. So my guess would be that if you have a bandwidth bound problem and you throw 2 threads at it, it's going to remain bandwidth bound. So there's nothing going to happen there. Here, if you're CPU bound and you still have memory bandwidth available using 2 threads, you should see some speedups. But you have to carefully make sure that you have enough memory bandwidth available. Otherwise, it doesn't. I mean, it's like it doesn't make sense to use SIMD instructions if you're bandwidth bound. It doesn't make sense to use multiple threads if you're bandwidth bound. So that's essentially the core of the problem.
One question. You said that you've used the Intel compiler.
Yes.
Have you tried different compilers, or would you expect that? Okay, so yeah, how are they different?
Well, intercompiler was the fastest, definitely. For all of my benchmarks, I did also with GCC, and intercompiler was clearly faster between, I don't remember, 20 and 50%, let's say. So that's why I just stick to intercompiler. And so, for example, if you look at here, the more than 4 gigaflops, I think it essentially means, even if I'm not explicitly using Simdi instruction, it already does some sort of Simdi. I get like 1.2 flops per cycle instead of the FPU bound of 1. So I already have some Simdi somewhere, and the Intel compiler is usually the best to make use of this. But if I explicitly target Simdi registers, I get like a factor of 3 more. And also, maybe I can comment on. So here I'm just showing the speed up for the 2 processors. If I actually look at real performance, the Xeons are like a factor of 6 faster than the Opterons in these cases. So here I'm just showing, I'm a bit favorable to the Opteron because I'm just showing relative timings. The actual run times of the Intel Xeons was much, much better in these cases. Okay, I think no more questions, and I thank you very much.